All right, so now we're going to continue talking about the inputs of the PayMinimi software. So we talked about the E-star. We finished E-star. What else is out there? Error voids and effective binder content are two inputs, and these are also significant inputs. These are inputs that are significant because they are related to the fatigue properties of asphalt mixture that we are evaluating. So effective binder content is the VBE, which is in the phase diagram. That's what VBE is. We talked about this yesterday. And error voids is this essentially. So VMA, remember, is VBE plus VA essentially. So these are significant inputs. And one thing to remember is VBE does not change with the compaction level. So once we have a VBE for a mixture from phase diagram, you may or may not remember from yesterday, but that VBE is constant, whether you compact too much or too little. So that means VBE is a property of the loose mixture. So depending on how you compact, VA will change, but VBE will not change. Error voids will change depending on how well you compact. So now VA, VMA, and VFA will change with the compaction level. VBE, if you know the VMA in the field, we can calculate VBE is equal to VMA minus VA. This could be calculated using the job mix formula. So if you have the job mix formula will have a VMA number and error voids number, which is the 4% typically designed. So from VMA minus VA, you can calculate the VBE for your mix. Once you know that VBE, that mix is constant, in the field, if you want to compact to 7%, 8% error voids, that's what you enter, whatever the compaction level you expect, and VBE is a constant number. Now, Poisson's ratio, unit weight, most people use default values for these. The results are not too much affected by these two. Now, let's go back all these inputs and let's see what else we have. Level 2 and level 3. Now, level 2 and level 3, you can see E-star is an input, but it is a crucial input in real input. It is calculated using a predictive equation. If you look at the input of the Mepdg or PayMinimi software, if you go to level 2, for example, it will ask you to find, it will ask you to enter the gradation of the mixture, only 4 of them, 4 of the sieves, person passing 3/4 of an inch, 3/8 of an inch, person passing number 4 sieve, person passing number 200 sieve. So once we enter these, the software will calculate an E-star for you based on this super simple equation. So this is called Witt-Sachs equation. It's a bit lengthy. You know, a whole bunch of gradation parameters and viscosity, AVTS relationship. So this viscosity comes from G-star. Just like we've done in the Excel sheet, viscosity is calculated for different temperatures in here. This is level 2. Again, that's what this equation that we used in our Excel sheet. Now we have E-star. In addition to E-star, another level 1 input is the creep compliance at low temperatures. These are used in low temperature cracking calculations. So -4 Fahrenheit, 14, and 32 Fahrenheit. So these are, if you look at this, loading is time, and this is the creep compliance. What is creep compliance? So when we do a stress control test where we apply a load level, just like we apply a certain weight to a material like this, we have a constant weight. If this is a viscoelastic material, strain response will be creep response. It will be creeping because of this load. And creep compliance is called D of T. D of T is essentially E of T, this curve, divided by this constant stress. So the shape looks identical to this, normalized by the stress level that is applied. That is called creep compliance. And this is obviously not megapascals, 1 over megapascals. sorry about the typo, please fix this. Creep compliance has a unit of 1/megapascal or 1/psi or 1/kilopascal or whatever the unit you use for stress. It's 1/megapascals. I need to remember to get these corrected sheets to my folder back. All right, so here's a simulation of creep, real simulation. So you have a load applied, and this is how the creep happens. This is actually creep and recovery because you remove the load, and this is how it actually recovers as well. All right, so this test is run on an indirect tensile mode. So we apply the stress to an IDT sample at low temperatures because this is a lot more convenient. We measure the strain on sample and we get this. Now, as I said yesterday, creep compliance and dynamic modulus, these are two viscoelastic properties and they are interchangeable. So you don't actually have to run the D of T to have the D of T. If you know how to convert E star master curve to D of T, you can do that. And that's exactly what we did for MDOT, for the project. So that has a database of a whole bunch of creep compliance values that are based on E star. So there's a mathematical conversion. But if you can run the test, but it's not required. You can convert. Conversion is not easy though. It's not like 1 over something or 2 over something. It's a bit lengthy to explain. I'm not going to get in there here. And then another input is indirect tensile strength. Indirect tensile strength at low temperatures. So what we do is we go to lab and we apply load at a certain constant rate of loading. We have load versus displacement. Maximum P is measured. That P divided by pi d dts is going to give us the IDT strength. That goes into a Mepdg equation. So this is the output of the PayMinMe software. This shows the plot of D of the creep compliance at different temperatures. This is 32 Fahrenheit, 14 and 4 minus. These are inputs that you were entered and it just plots out. And also IDT strength is also shown here. That's an input that you were supposed to be doing at the beginning. Now, takeaway so far, E star is one of the most important inputs for PayMinMe. E star is used calculation of fatigue cracking and rutting, and not in thermal cracking calculations. D of T is used, creep compliance is used, and creep compliance and E star are interchangeable. If, only if, the test is run properly. Of course, E star, you need to have a really good E star measured. Okay, if you look at, again, we are going back to the tornado plot, and there are some other inputs such as heat capacity and thermal conductivity. You can see they are far down, so they are inputs, they are important, but outputs are not sensitive. So not really, pretty much nobody changes them. Justin, you use this all the time. Do you change them at all?
No, we don't.
You don't. You use those numbers. Okay. Yeah, I have never seen anybody trying to find those numbers because they are not sensitive. Outputs are not sensitive. How about unbound materials, soils, subgrade, and so level 1 input for unbound. Originally, when they were coming up with PayMinMe, they were thinking of a nonlinear finite element that considers nonlinearity of the base layer. Unfortunately, they decided to give up, so they did not include finite element to include the nonlinearity of the base. What is nonlinear? When I say nonlinearity of the base, this is what I mean. Soils, their response, their stress-strain response, and their modulus is directly related to the confinement level and how much stress that they are experiencing. If they are nicely, tightly packed, their stiffness will be high. If they don't have enough confinement, their stiffness will be low. This is logical. Anybody in soils area knows all about this. It's an important input, but unfortunately at the moment, it's not included in PayMe. And the reason is I don't think anybody came up with an efficient nonlinear model to do this. Level 2 and level 3 exists in PayMe, and the main input is the resilient modulus. The resilient modulus is recorded at optimum moisture content at a single stress state, or MR at different months can be also entered. So if you want to include the variation of the resilient module with different months, if you know because of the rain condition and how much saturation, if you know like the change in moisture content versus the resilient modulus, then you can enter all that, and that will be a lot more accurate. Level 3 is a single resilient modulus. For stabilized materials, there are no different level inputs for the material. Essentially, elastic modulus, minimum elastic modulus, modulus of rupture, thermal conductivity, and heat capacity. These are the materials like for cement-bound materials or those kind of stabilized materials. Those are the only inputs. So here's an example snapshot of any click unbound material. These are the options that you can see. And you can actually calculate the resilient module from CBR, R value, layer coefficients, DCP number, and PI gradation. There are some empirical relationships that are embedded into the PayMe. You can calculate all that. Traffic. Traffic is going to take time. So let's take a break.